Hello. Sorry to break into the conversations. I'm sure it's a happy setting this afternoon because you're inside where it's warm and not 8 degrees outside or 10 degrees, whatever it is. So welcome this afternoon to the Jones Seminar here in the Thayer School. Our speaker this afternoon is talking about a healthcare systems, healthcare delivery systems topic for us. Jim Benneyan, Associate Professor at Northeastern University in the Mechanical, Industrial, and Manufacturing Engineering Department. Among other things and other titles that Jim holds, he's also the Executive Director of the Veterans Administration New England Healthcare Engineering Partnership. He's the co-director of a National Science Foundation Center for Healthcare Organizational Transformation. And in his academic work, he's published in areas of healthcare systems engineering, statistical quality and safety methods, computer simulation and models, as well as risk-benefit analysis and probabilistic optimization. Jim's expertise in the area of statistics is what I've known him for over the years since I first met him. And his applications in the healthcare delivery systems are really of strong interest to us. He's published significantly with 75 papers and won awards in both research and teaching. He was, before joining Northeastern, he was a senior systems engineer at Harvard Community Health Plan. And he was also past president of the Society for Health Systems, and he's a fellow at the Institute for Healthcare Improvement. So if you'll join me in welcoming Jim to give us a talk on his work on systems engineering analytical models of heterogeneous healthcare evidence-based adherence. Thank you.
Here you are. Thanks. Okay. Thank you, Bob, and thanks everyone for coming to share some of your time this afternoon with us. I'm honored to be here speaking with you. I think my perception is that we have sort of two audiences. So I have a somewhat complicated title, but it comes down to variance and heterogeneity. So I think we have people from the engineering community, and my sense is, given the focus, some people from the healthcare community. So I'm going to do my best to try to serve both audiences and provide sufficient sort of context and background so that we can sort of both see where this is all going. So I apologize in advance if I sort of belabor something that may be particularly obvious to you, but perhaps not to some of the others. So in terms of a roadmap for where we're going, I want to divide this talk into thirds, roughly. So I want to spend a fair amount of time setting the context and talk about a particular problem in the healthcare system. So the problem has to do with heterogeneity, with compliance, with adherence, with variability, which is widespread with profound consequences everywhere. So I want to spend some time framing that up. Fundamentally, I'm an engineer, so I want to talk about some of the work we're doing in my group to try to approach this problem. And we're working on a variety of things, but I want to focus in on a particular probability model that we've developed and talk about how that interrelates with some of the other work going on in the healthcare process improvement community. And then I want to be sure to step back and talk about the implications and why I feel this is not just an academic exercise, but is important to the other work going on to improve the quality and performance of U.S. healthcare systems and worldwide. So I'm running a test right now, seeing if this pointer system is working, and I think it's working fine. So that's the roadmap of how I'm hoping to structure this time. So before I jump in, let me just sort of ground us both in healthcare systems and in systems engineering. So I'm an engineer, a systems engineer specifically. My background is mathematics and computer science, and I reside in an industrial engineering and operations research cluster. And this type of engineering, what we are interested in is developing models, mathematical models, computer models, physical models, graphical models of systems, processes, and using those types of models to understand, improve, control, and optimize systems, processes. So when I talk about systems engineering, I know that that phrase can mean different things to different people. That's what I'm talking about. So in healthcare, industrial engineers, systems engineers, people using methods to improve processes. This type of work's been going on for at least a century, both at sort of the micro, mid, meso, and macro sort of national levels. Everything from looking at appointment access, scheduling, layout in a particular department or microsystem or organization, to looking at more macro regional issues in terms of where do we locate what types of services, to looking at sort of national problems, policy, screening, outbreak detection, things like that. So I have an incomplete history of systems engineering in healthcare, and this is an incomplete, very abridged version of that history, but you can see some of the areas that we've worked in and the type of work, not me personally back in 1911, but people in our community. Surgery, nursing, quality control. Dr. Deming, those of you who are familiar with quality improvement and control charts, was applying SPC to healthcare problems as early as the 1950s. Queuing, waits and delays, computer simulation models to try to make healthcare systems work better, and so on. And recently, there's just been a huge interest in applying methods used in manufacturing and other industries, which I would just call frontline process improvement methods. Six Sigma, that comes from Motorola and Xerox, and more recently, General Electric. Lean, which is really an adaptation of what Toyota would call their production system, and methods like that. So just some quick examples to frame this, and then I'll get on to the focus of this talk. 3 examples of operations research or systems engineering in healthcare. On the left, looking at surgery appointment scheduling in terms of which surgeries are scheduled for which OR rooms, trying to really optimize the system. When should we schedule each procedure in which room and what start time to be most efficient? And there's a mathematical model to approach that problem. Computer model to look at patients flowing through a particular system, looking at efficiencies and how many resources of what types should I design in to evaluate the overall goodness of the process. And in the lower right-hand corner, sort of more macro or policy issues, looking at some mathematical models, here using graph theory to try to provide some analysis that will inform policy decisions about organ sharing. So that's kind of the community that I normally live in, just to sort of frame this. This is another example. We're doing a lot of work recently looking at traumatic brain injury. Brain injury, big problem coming out of our modern conflicts. RAND estimates about 20% of all returning U.S. servicewomen and men suffer some degree of brain injury. So the fundamental question is, from our community, can we do a better job at predicting who's at risk, categorizing them from low, medium to high risk, figuring out what types of services, medical services they need, and then ultimately taking that information and, given finite resources, trying to optimize the use of those finite resources. Where should we provide what types of services across the United States to best meet the needs of our veterans? And this is a mathematical model, it's a quadratic programming model that is optimizing what services are provided where. So that's the type of work we're doing. So let me talk about the healthcare context specifically, and this particular problem of heterogeneity and of compliance or adherence. And I want to spend a fair amount of time framing this up. Big picture first is, our system is riddled with opportunities. is the best way to say that. The World Health Organization evaluates the U.S. healthcare system, this is several years ago, near the bottom of the first quartile in terms of all of the countries, first, second, and third world countries in the world. An organization called the Commonwealth Fund, a nonprofit, annually is comparing, doing a lot of analysis of the U.S. healthcare system as well as comparing our system to reasonable comparators. On a scale of 1 to 5, 1 being the best, we consistently rank last or next to last across many dimensions. These are the Institute of Medicine dimensions of health, essentially: safety, patient-centeredness, access and timeliness, efficiency, effectiveness, and equity. So we're not the best by any stretch, yet we cost the most per capita of any healthcare system in the world. It's estimated that the cost of healthcare in this country is roughly 17% of our GDP. By 2020, it'll exceed 20%. Healthcare is the single largest industry in the United States. It's also estimated that, depending upon the study, and this has been replicated time and time and time again, 15 to 35% of that total cost is due to inefficiency, scrap, rework, redundancy, poor designs, poor quality, and so on. So there's enormous opportunity there. We're not the safest system by any stretch. There are patient safety problems in abundance, and I'll talk a little bit more about that. There have been many, well, let me leave that for a minute, but many studies estimating the consequence of harm in U.S. hospitals. So in the lower right-hand corner here, what are we doing about it? The Institute of Medicine, the IOM, which is sort of a parallel to the National Academy of Engineering. I mean, it's one of the academies commissioned by the U.S. government, has been studying the performance of healthcare systems for a long time, and some of these reports are sort of famous in the healthcare community. When somebody refers to something as the IOM report, well, there are dozens of reports coming out every year, but they're talking about a particular report called The Air is Human in 1999, first sort of documented and collected all of the studies that had been done prior to that, articulating and trying to bring some focus to patient safety problems. So we have quality problems, patient safety, drug safety, studies of emergency departments, and in the lower right-hand corner, a publication talking about we should be doing more to study the performance of healthcare from a systems engineering perspective. So in my community, when people refer to the IOM report, they're talking about this one down here in the patient safety community in healthcare. When they talk about the IOM report, they're talking about the one immediately above it. So in summary, significant variation just abounds. A variation in the performance of our processes, in provider practices, in patient compliance. It is everywhere, and it's just exacerbating the performance and quality and outcomes of our system. So some examples of that. In the upper left-hand corner, this is just one example I clipped out of work of a group here at Dartmouth called the Dartmouth Atlas. Wenberg for years and colleagues years has been studying the variation in practice across the United States in terms of cost of healthcare, in terms of types of procedures followed, and so on. So you can go online and look for more information, but this is just one example, a map of the United States, and this example is looking at the percentage of breast cancer patients who are receiving a particular type of surgery versus not. Here, breast-sparing surgery. So color code indicates percentage, and literally we're ranging from about 2 to 20%. So widespread geographic variation, even within a particular state. Maine and Iowa are two examples here. The percentage of men and women by a certain age that are receiving a particular procedure, widespread variation. Average length of stay, number of days in a hospital in rough roughly some of the 80 odd best hospitals in the United States in the last 6 months of life, ranging from 8 to about 30. And then I'll talk a little bit more about compliance to the, I'll talk a lot more about compliance to the evidence base. But it has been estimated in several studies that in terms of providing patients with all of the elements of care that we know we should be providing, that roughly we get that right across acute care, chronic care, and in preventive medicine 55% of the time. So non-adherence on the left, just a little more detail on that, often referred to. Beth McGlynn has the most famous study of this in terms of some of the conditions we're looked at. And I'm going to come back to what's behind some of these numbers. But here you see 30 to 65% of the time we're actually giving patients with these conditions all of the care elements that we know we should be giving them. And on the right-hand side, hand washing compliance in hospitals, of course. The lack of adherence to hand washing really is the low-hanging fruit in concept, but not in implementation. One of the number one drivers of the spread of infections, nosocomial infections, hospital-acquired infections. This is a hospital we're working with as part of a collaborative effort with about 24 other hospitals, looking at some of their compliance data over time, and it's trending up a little bit, exhibiting some variability, but roughly 50% compliance to hand washing. And this is those 2.5 hospitals, a plot over time of the minimum and the maximum. So compliance ranging from 30% to the upper 90s%. So a lot of variation. And we know we should be washing our hands. We're just not doing it all the time. So it's not all that bad. There's some things that the healthcare system is very good at in terms of 1 in a million failures or happen very rarely. Very rare events are a problem, but thankfully they're very rare events. But still, some things that are happen just with unacceptable frequency. And this is in the order of magnitude of, say, 50%, 60% compliance. These types of conditions in hospital readmissions are often driven by non-adherence to things we know we should be doing. So this is the Institute of Medicine report called "To Err is Human," and this links to what my colleague Vin Sani and many others often refer to as closing the knowing-doing gap. How do we do a better job at doing what we know we should be doing? And so here are some of the statistics in the IOM report, which actually did a nice job at summarizing research of other folks, Lucian Leap, David Bates, and a whole host of other people who for years had been documenting studies in terms of the frequency, severity, and costs of error in healthcare systems. So I'm not going to step through all these numbers. You can look at them. There's some disagreement about these numbers, and other studies have been done that are either slightly larger or slightly smaller. But for the purpose of this talk, these figures are staggering, with significant consequences in terms of quality of health, mortality, and costs. So let me give a couple of examples of non-adherence. So one of the things that we know we should be doing in surgery is giving antibiotics prophylactically. Optimally somewhere between 30 and 60 minutes before the first incision, so that the antibiotic has time to perfuse through the tissue and get to the site of the incision and do its work. So here's some data from a hospital I worked with years ago on the timing of the antibiotic before first incision. And so right at 60 minutes, so this window here is the optimal window. This is actually 0 to 60 minutes prior to the first cut. And you can see that a huge percentage of the time isn't within that window, either being administered far too late or far too early. So you think to yourself, well, how difficult could it be? But this is an example of something that's known that should be done, that for one reason or another in the design of the system just isn't being done 100% of the time, much less, I would say, of this whole mass of this probability distribution. It looks to me to be about 30% of the time we kind of hit between the goalposts. Unplanned readmissions are roughly a $20 billion problem. Some of it, not all of it, is causality is linked to non-adherence. Non-adherence on the part of the provider, non-adherence to appropriately communicating to the patient what they need to be doing on discharge, communicating those discharge instructions, and then once the patient is home, not following those instructions, or the family just not complying. So again, a huge problem. No better, it's tough for us to point fingers at our providers if we're not doing a better job. Diabetes management is a nice example of that. Again, the cost of patient non-compliance is staggering. I mean, absolutely staggering, $180 billion. Okay, so what's being done? Well, lots of things are being done, and I think what's really going on is a lot of frontline process improvement in the trenches, quality improvement work. So if you're familiar with or have been exposed to Six Sigma or the Deming philosophy or quality management or continuous quality improvement or the Plan, Do, Study Act or Lean, the Plan, Do, Study Act cycle or Lean or the Toyota production system, there's sort of a tsunami of this type of activity going on in healthcare, and a lot of training and a lot of efforts to spread this type of work, to put everybody to work who works in the processes routinely, who will understand, you know, these seemingly trivial reasons that these care practices aren't being followed, and design systems where we adhere to these care practices a lot more consistently. So that's probably the most powerful work going on. What I want to do is spend a little bit, a fair amount of time talking about bundles. And a little bit of time talking about risk adjustment and their use to evaluate the quality of healthcare systems. So for those of you who don't know, for those of you who know, this may seem like I'm providing a lot of information, but let me make sure you understand what a bundle is. So, and I'm going to be a little agnostic here in terms of nomenclature. So core measure sets, bundles, and several other terms are used. And for purists, there's sort of a little bit of a semantic distinction between these things. For purposes of what I'm talking about, they really are all the same. So the idea of a bundle is a handful, 3 to 7 elements that we know we should be doing for our patients. There's excellent research in the literature, peer review, randomized, controlled, blinded study, level 1 evidence. There's really no debate. You know, the antibiotic example is a good example. Broad consensus, nobody's disagreeing with the science, just not getting implemented. So to prevent SSIs, surgical site infections, there are variations on this, but here is one bundle of care elements. I already talked about administering the antibiotic within the right window, how we remove hair, if at all, from the site of incision. Actually is important, and historically a lot of hair removal is done with razors. We all know what razors and razor blades are, but there are campaigns in hospitals to remove and find those hidden razors in drawers in doctors' offices. You just shouldn't be removing hair with razors. You should be either not removing it or removing it in a non-abrasive way with scissors or something like that for just that purpose. Microscopic abrasions to the dermal barrier will allow the bacteria to invade and do its damage. So we know that these, and the other two have to do with proper control of the patient's body temperature and blood sugar, and there are others. But this is a bundle of 4 elements that should be followed for every surgical patient. So how these bundles are being used currently, and probably with increasing frequency in the future, is to compare organizations and rank them, to evaluate your own organization or practice to see if you're trending better or trending worse, you know, and sort of monitor and verify whether in my Six Sigma type of work, my frontline process improvement work, I tried something. Did I get better or worse? Well, did our bundle get better or worse? And I'll talk about how specifically we measure that metric in a minute. And then of possible concern, but certainly something that's being piloted and put into practice, is the use of performance of the bundles to externally incent organizations, either through public reporting, through incentives, penalties, financial penalties, and pay-for-performance schemes that will reward the best performers and undercompensate the worst performers. So there have been pilot studies that have been done to evaluate whether this would be effective carrot and stick way to get hospitals to perform better. The most well-known one was a partnership between CMS, the Centers for Medicare and Medicaid, and Premier Healthcare Alliance, which is a large purchasing group for hospitals, just did a pilot study and sort of pretended that they were going to be paying for performance according to performance against the bundles. So that theme is out there, and it's quite likely to be part of our future. So I think it's important to talk about how we evaluate these bundles. You know, when you look at data and ask the question, are we better or worse, fundamentally that's a statistical question. I mean, absolutely. It's just whether you answer it using statistics, you're basically looking at data and saying, is it better or worse, and somehow cognitively ascertaining whether that difference is small, just in the noise, or of practical importance. So here are some examples of bundles. These are sort of the first generation of bundles. There's a second generation, and probably we're into the third generation. But VAP is ventilator-associated pneumonia. This is joint replacement, knee and hip total joint replacement, community-acquired pneumonia, congestive heart failure, acute myocardial infarction, and bypass. Coronary artery bypass. So here are anywhere from 4, well here are 3, 7 bundle elements in each of these conditions. And I'm not going to go through them all in any detail, really. Ventilator-associated pneumonia, elevating the head of the bed, so if you're mechanically ventilated in an intensive care unit, to prevent ventilator-associated pneumonia. And I should have called your attention earlier to the average cost of a VAP is huge, and mortality rates associated with patients who develop vent pneumonia is a huge concern also. So elevating the head of the bed, sedation vacation relates to routinely, regularly, daily ascertaining whether the patient can be weaned from ventilation, because the longer you're ventilated, sort of the worse off, particularly in terms of developing oral ulcers and blood clotting. So one comment to make, some of these elements may be of greater clinical importance than another, and I just plant that seed for passing. And notice in the square boxes, a lot of these elements are time-based. Did I receive something in the right time window? Did I receive aspirin within 24 hours, or beta blockers, or thrombolytics within 30 minutes? Was my oxygen assessed within a particular time window? Did I get my antibiotics within 4 hours, and so on? So there's this sort of threshold-based component to some of these elements, and I'll come back to that. So this is the first generation of bundles advocated by CMS, the joint commission that accredits hospitals, much like in engineering we have the ABET accrediting organization, the American Hospital Association, Leapfrog Group, the Institute for Healthcare Improvement, many of the leading organizations driving this type of work. We're advocating these bundles a long time ago. So here's an example of compliance to the VAP bundle. The rows, these are different intensive care units and critical care units. So here, let's look at the CCU. Here are really 5 elements to this bundle: head of bed elevation, these types of prophylaxis, and so on. And variability. So heterogeneity is sort of the common denominator theme to this talk. Compliance. 84% of patients are having the head of their bed elevated, either at all or to the appropriate recommended angle. 99% are receiving prophylaxis for blood clotting. 30% are being daily assessed and sedated to see if they're ready to be extubated. Somehow they've broken these out into 2 elements. 60% are being assessed for extubation. 66% are the total number, well, I'll come back to where this 66%, but 66% are receiving the total bundle. And how that number is computed, I'll come back to that. But we can compare these 5 critical care and intensive care units and say which one's best by looking at these data. If they were 5 different ICUs in 5 different hospitals, we can say which one's best, which one's worse. If these were 5 different months in time, we can say, are we getting better or are we getting worse? But we need to put that in some sort of statistical framework, I think, to draw a valid conclusion. So that's just an example. So here are some plots of compliance over time, one hospital, which I'm just calling H1, in terms of the percentage compliance to discharge instructions, informing the patient of everything they should be doing after they leave the hospital. And things are getting better over time, and these red lines are control limits. If you're familiar with statistical quality control charts, that's what those are. If you're not, they're basically probabilistic thresholds that indicate statistical significance. If the data fall outside of those limits, statistically, in a significant way, things are different. If they don't, it's just white noise. So counseling to stop smoking. On the right-hand side, these are plots of 4 different hospitals over time in terms of compliance with the bundle for heart failure, and you can see 2 things. Over time, any given hospital is varying, and between hospitals there is a variability also. So again, I'll come back to that. So a lot of the work that's going on can be put in the following framework. Maybe not formally like this, but it is essentially this, and this is the frontline version of the scientific method, really. The plan, do, study, act cycle. Let's identify something that we think will make a difference. How could we get people to wash their hands more frequently? Let's do it and execute some sort of plan. So in science, this might be some sort of randomized study. Let's analyze the data in the study quadrant. And based on what we learn from the analysis of the data, let's act on it. So whatever our aim is and whatever our measures are, here the measures are compliance to the evidence base. Let's try something. Either it's recommended to us or we've had some sort of brainstorming aha moment, and see if we get any better. And the whole context that this is done in within healthcare is in this mental model of rapid cycle tests. And the more we can test and quickly decide whether to uptake or abandon an idea, the better off we'll be. So repeated tests of change over time over and over again is the roadmap to improvement. And a big framework that this is done within healthcare is there's a lot of collaboration in healthcare. So one might assemble 2 to 4 dozen hospitals who are all interested in a particular problem, and over the course of a year work on a particular problem, try things locally, share things with each other, what's working, what's not working, let's look at the data, and collaboratively work on problems. So this whole idea was somewhat invented by the Institute for Healthcare Improvement, and really a part of the genius behind this was Paul Batalden, who's here at the Dartmouth Institute. But the whole idea was we would have a lot of breakthrough this way if we had dozens of hospitals working on a common problem, and we were providing training in these learning sessions spaced at 3-4 month intervals, and then back in their institutions they were doing a lot of tests of change and ascertaining whether they're working or not, sharing them with each other so we can spread what works quickly. So I'm belaboring that point because we have these, the mantra is rapid tests of change. Let's look at a few pieces of data quickly and decide, hey, this is good or it's not working. That's in the check. And then in the act, spread it. So a big dissemination component. So testing, learning, and spreading is the overall idea here. The question is, how do we discover ideas? We perhaps don't do enough statistical evaluation of the data after a test of change, but we're all making decisions as to whether to accept or abandon. There was an article about a month ago by Atul Gawande in the New Yorker, who is an independent, wonderful voice in the healthcare safety and improvement community. And as a resident was talking about harm that he was seeing all around him and drawing attention to that. But he's basically saying the same sort of thing in different words. The name of this article is testing, testing, testing. The more we can test, the faster we can learn. And I think his phraseology was, let 1,000 flowers bloom. If we plant enough good ideas, something will germinate. So that's the context. Whatever it is that we learn, let's spread it. Let's standardize locally, disseminate broadly, and drive into practice, one way or another, intrinsically or extrinsically, in lots of ways that could happen. The IHI, Institute for Healthcare Improvement, several years ago, was getting frustrated that things aren't moving fast enough. So it came up with this idea of a patient safety campaign, and improving some is really not a reasonable target, and improving some day is not really a reasonable goal. We need to have a little bit more specific focus than that. So the challenge was, could we reduce caused mortality in hospitals due to harm by 100,000? Could we save 100,000 lives in an 18-month time span? So that's called the 100,000 Lives campaign. Lots of ideas that were developed in this type of context were pushed across the country through a whole network, much like a political campaign. It's fascinating. In the end, it was estimated that about 90% of all acute beds in the U.S. were in some way touched by this effort. So that's the context. But I want to come back to, how do we know what works and what doesn't work, and how can we spread what we know works as quickly as possible, and also not spread things that don't work. So there's a testing need framework. So here is the ventilator-associated pneumonia bundle, and it's a pretty reasonable question. We could have Hospital 1 versus Hospital 2, those are the two columns, or this could be in my organization before an intervention and after an intervention, and percent of a sample of patients that the head of bed was elevated properly before and after, and this is just a sample of patients. So the question is, are we any better, or is this due to white noise? And then you have the whole bundle of elements, and the question is, are we any better or not? So this relates to type 1 and type 2 errors. It relates to sensitivity and specificity. So that's a type of question that we want to answer. We'd love to develop confidence intervals, whatever that means, or hypothesis tests for bundle improvement. We'd love to develop control charts, if you're an SPC, statistical process control type of person, for monitoring adherence, bundle adherence. And there are simple types of control charts that were developed by Walter Schuhart in a manufacturing context in the 1920s, and more advanced types of control charts. And several people may be familiar with what's called a Q-sum or a cumulative sum. The theoretical basis for that is what's called the likelihood ratio test, but a very powerful method that will detect changes, improvements or non-improvements faster. So if the notion is let's accelerate the improvement of healthcare because we've got to get better soon, one might want to develop this type of methodology for specifically the bundle adherence type of setting. So that's a statistical kind of desire. Let me just ground us and remind us about a statistical fact. And George Box said it best one time. George Box is sort of a statistical luminary in my mind. Where he basically said it's a statistical world and you need to frame your interpretation of information in that context. So here is what is called an operating characteristic curve, and I'm going to end this talk showing you some OC curves. So I want to just give you a little primer here and explain how to interpret this curve. Narrower is better. Narrower means faster detection, better sensitivity, better power. That's the gist. So if where I have this blue line, vertical line, is our current performance, if we get a little better or a little worse, vertically, this is the probability of saying there's been no change. That'd be up here, 100% probability there's been no change. Or this is 0% probability of concluding there's been no change, or things have gotten better. So if I improve from this state to this state, I'm a little better, and the probability of saying I'm better is roughly 50%. This would be a good method. If I were using some other method that's represented in dashed lines, if I improve the same amount and look at some data, the probability of concluding I haven't improved is about 95%. So you have a 5% chance of catching it, 95% chance of abandoning a really good idea. So this is a good method, the tighter curve, and the wider curve is not so good a method. So a holy grail in statistical methods is always to come up with something that has the best OC curve. I've got some pretty good ones, but if you can come up with one that's better, that's great, good contribution. Then let's retire my methodology. So the other way to look at these OC curves is in terms of average run length. The way I presented it was for a one-time hypothesis test. If you're monitoring performance over time, like in a control chart, we would often talk about average run lengths. That's the expected time until I conclude there's been an improvement or a deterioration. It's basically the reciprocal. So if the probability of concluding there's been an improvement is 50%, the expected time is 2 plotted points. And if you're plotting data monthly, that's 2 months. You made an improvement, it'll take 2 months to find that improvement. If the probability of concluding there's been an improvement is 5%, so it's the reciprocal of that, so it'll take 20 plotted points or 20 months. So the time until we verify that a test of change that makes a difference, and the time until we conclude it actually does make a difference and should be shared, if that's 20 months, chances are you're going to abandon that, unfortunately. So that's basically the fact. It's the statistical world. There's nothing you can really do about it. You just need to interpret data and know that every time you're looking at data, you incur some probability of a type 1 error and a type 2 error, falsely concluding something's a good idea and falsely concluding something's a bad idea. So in this testing over time context, we're plotting data and we're doing tests over time, rapid cycle tests. We're looking at 2 or 3 points, making a conclusion, standardizing and spreading or abandoning. So when you frame that up against what we know, the fact of average run length, there's a disconnect there. The question is, in this time series, where, if anywhere, is there an improvement? So I want to talk about what we've been doing looking at adherence, sort of broadly, but come back to this bundle thing really quickly. So we've been doing a little work. This is joint work with my group, and Archie is the Regent Streif Center for Healthcare Engineering at Purdue, some colleagues in that center. And we've been interested in this whole issue of unplanned, unnecessary hospital readmissions and trying to develop some sort of engineering models to try to inform all of the study that's going on in those contexts. So I'm not going to do a deep dive on any of that, but we've been looking at measurement paradigms, but also can we develop computer models, Monte Carlo models, or some sort of stochastic model that accounts for the variability as patients are discharged, transition through various states of health, and at some point in time may need some type of intervention. A visit by a nurse, some sort of home health, telemedicine, or readmission. And can we develop those types of models and use them inform and optimize when we should perhaps be pursuing particular interventions. So it's all sort of preliminary research, that's why it's called research, and we're just trying to experiment around and see what might be of use. The whole spectrum, even feedback control, if there are electrical or mechanical engineers in the audience, you know, feedback controllers where you're looking at data and deciding how to make compensating adjustments up or down. And again, George Box did some wonderful work looking at deadband feedback control methods, and we've been looking at the application of them in the diabetes context. But I want to come back. All of that, I would love to talk more and more about that work because it's technically challenging. But the thing I keep coming back to is the measurement piece. Somewhat because of its importance, and I think because of how it interrelates with all of the process improvement work going on in healthcare. So, to compute compliance to a bundle, let me explain. There are really 2 ways that that's done. But suppose you have any given time, a week or a month, we took a sample of 10 patients. And let's just look at patient 2. And let's consider one of these bundles where there are 4 care elements, element 1, 2, 3, and 4. And element 1 was followed, as was 3 and 4, but 2 was not, right? So 3 of the 4 elements were met. Not all of them were met. As opposed to patient 1, all of the elements were met. And patient where do we have one? 6, where 2 of the elements were met. So of course, if I just told you 2 of the 4 were met and you didn't have this table in front of you, the question is which of those 2 or 4 were met and how many different ways could any 2 of the 4 be met? And it's combinatorial, factorials, 4 choose 2, and there's 6 possible ways that could happen. But fortunately we have the data in front of us. But over this whole sample of patients, there were actually 40 opportunities to do what we know we should be doing. And over those 40 opportunities in this example, 30 of the 40, 75%, we did. So that is actually, down here, this 30 over 40, that is actually the bundle compliance metric. Sometimes it's called the composite metric. So we're going to record for all of these measures, or you're going to record in your process improvement work, compliance this way. So a couple of things to point out. One is, in this example, compliance in the sample is 90% for this element and 60% for this element. And so there's heterogeneity. We don't consistently, it's not like we're 50% compliant on all the elements or 95% compliant on all the elements. There's heterogeneity in the probability of getting some of these things right. Some of them just seem to be more difficult to do. So this 75% is the compliance for these 10 patients. It's not really the true compliance rate, it's just an estimate. But I'm going to call this thing F. So we have some notation. It's really F hat, where hat denotes an estimator of the overall compliance to the evidence base. And every time I take a sample of 10 patients, obviously my calculation of F is likely to be different. So I'm going to have a lot of estimates over time and try to aggregate them to estimate the overall compliance rate. Now, the other way that compliance to bundles is increasingly being measured and advocated to be measured is this thing called an all or none or all or nothing. So patient 1 received all 4 recommended elements of care. So let's count them as a success. Patient 2 did not, so they're, or we're a failure. Patient 9 did not also, and they're an equal failure. Actually, they're more of a failure because less of the elements were met. But we're just going to count the number of patients that got everything. And that's the all or none. And it's always going to be less than or equal to the composite measure. But that's another way. And I'm not going to focus so much on that herein because it's widely advocated, but not as strong a measure. The composite measure really is certainly what I recommend, and I'll come back to why. So here's a VAP example, ventilator pneumonia. Here are the compliance rates of a particular hospital, masked here, and you can see the variability. We're going to have data in this type of format, and again, the compliance rates are going to be different for each of the elements. And we're going to know these composite scores, and we're going to want to plot them on some sort of control chart, which is just a metaphor. You could use compare confidence intervals, you could conduct a hypothesis test, or whatever. We're going to subject them to some type of statistical test to see if there's a difference, whether we're getting better or whether we're not. And we'd like to do that hypothesis test or analysis of variance type of thing, although it's not clear to me how one would do that, or plot that control chart, calculate those limits so that they're correct, so that we make the right decision most often. So how exactly we do that is sort of the open question. So this is the type of data we're dealing with, and it's very similar to another issue in healthcare, which is if we're going to track surgical site infections as an outcome or mortality as an outcome, we have to account for patient-to-patient differences. We have to adjust for acuity. We have to do risk adjustment. One hospital may just have a lower survival rate because it's seeing sicker patients. So we have to equalize things a little bit. Let me go to this slide. So there are 2 ways to do risk adjustment, and there are lots of methodologies that have been published for this. On the right-hand side is a surgical site infection example. So in any given week, category 1, 2, 3, 4, 5 are strata. Low risk, medium risk, high risk, and extremely high risk of a surgical site infection. And there's an algorithm for placing me or you as a patient into one of these buckets. And so those are the lowercase n's, how many patients are in each category. And then the lowercase x's, in this case, of the 41 low-risk patients, how many developed the surgical site infection. And over here is the total number that developed the surgical site infection. Right, so this is not unlike, as a matter of fact, it's identical to the bundle issue because we have the percent of all of the opportunities in this column that actually occurred, and the percent of all the opportunities in this column that actually occurred, and so on, where the occurrence probabilities in each column here developing a surgical site infection, in the other context complying to the evidence base, those probabilities are different. So that's the heterogeneity issue. So here's sort of the general context for that. The other application is something like a logistic regression model where for any given patient, given my condition, age, gender, family history, comorbidities, or whatever, you can actually predict or compute a probability for me. So we all would have different likelihoods of developing an SSI or surviving a procedure if you knew enough about us. So there are basically an infinite number of categories, and we all have a sample size of 1 in each category. But the general context is down here. One way or another, we're stratifying patients into categories, and we'd like some sort of aggregate method where we can look at outcomes really in the aggregate and ascertain whether things are getting better or worse. In a control chart context, hypothesis test, confidence interval, using sequential probability, I keep losing my mouse, I'm sorry, ratio tests or something. So this is just an example of that with one of the more recent risk adjusters for mortality, where every patient has a different predicted risk of mortality, and the outcomes are zeros or ones, denoting survival or non-survival. So risk adjustment is an important issue in healthcare, and there are lots of methods, and this is essentially, with apologies, how they all work. So we need to talk a little bit about Bernoulli and what a Bernoulli trial is. And I love this particular cartoon because I work with a lot of mechanical engineers and aerospace engineers, and it means something completely different to them than it does to me. So in Foxtrot, this individual launches an airplane, and just a paper airplane, and just sort of lets it go. And eventually, it gets tangled in his older sister's hair, at which point he says, hey, don't blame me, blame Bernoulli. So not knowing how many engineers we have, think, what does that mean to you? So Bernoulli, there are actually 5 Bernoullis, 4 brothers, I think, 5 brothers and cousins, and in mathematics and science. The famous one that the mechanical engineers think about is the person that derived a lot of the formulas having to do with flight and airflow. The Bernoulli that I think about is the probability guy. So a Bernoulli trial is, in my world, is a coin toss or a patient. So a coin toss is a head or a tail. It's binary. So we could call these things binary trials. A patient develops or does not develop an infection. A care element is or is not delivered. You're pleased with the decision to attend this lecture or not. All of these things are Bernoulli trials, and that's what a Bernoulli trial is. So really, I attempt a basketball shot, and I make it or I not. I don't. I try to kick the field goal in this game coming up, and 3 points or not, and so on. So those are all Bernoulli trials. Fundamental building block of really, of almost all statistical methods. The common assumption is IID, independent and identically distributed. Every time I try to kick that football through the goalpost, I have the same probability of making it or not. If I'm the same distance and the wind conditions and the pressure is the same, maybe that's true. But actually, it's not true. Every time somebody attempts to kick a ball through the goalpost, you don't have the same probability of success, because the consequence of that outcome may be different. So you may be feeling pressure, wind conditions may be different. You're 20 feet. You're at the 20-yard line or the 60-yard line, probability is different. So same thing with patients, right? The probability of surviving the procedure or developing an SSI is different. So we don't have IID Bernoulli trials. Same thing for the bundle compliance measures. The probability of administering discharge instructions is a lot different than the probability of some of the other elements. So means is all of the standard methods that we use to evaluate a collection of binary data technically don't apply. We can't aggregate data and invoke any methodology that's based on the binomial distribution. Does it matter? I mean, technically that's true. Does it matter? How much does it matter? And what should we do differently? The approach that I want to at least step you through here is deriving the exact probability distribution. So if you have a collection of 10 patients and they all have the same probability of survival, the number that survive can be described described by a binomial distribution. If I administer if I have so many patients who are all candidates for a collection of care processes, and the probability of administering correctly all those care processes is the same, the number of opportunities met follows a binomial distribution. But once we throw away that IID assumption, the the bundle compliance doesn't follow a binomial distribution. So what's of interest is developing a probability model. So we just had a paper published, I think it'll be out next week, that derives all of this. But I want to just step through it quickly. T and F. F is the compliance rate that we observe in a set of data. And we can basically ignore the W. The W is if we chose to put different weights on the importance of different elements. But if this is our random variable that's going to change from patient sample to patient sample, we'd like to know something about the mean and the standard deviation. We'd love to know the probability distribution, the exact distribution. Well, if there was some simple way to approximate that distribution, because it could get complex. So since up here we have basically the sum of random variables that within a particular element actually are IID. So every time I have a patient, the probability of following any particular element is consistent from patient to patient. The number of times I do that does follow a binomial distribution. So I have the sum of non-identical binomial random variables is what's going on here. So we know some things from probability theory. The mean of the sum of binomial random variables is the sum of the mean of those random variables. The variance of the sum of binomial random variables is the sum of the variances. The probability generating function of the sum of any number of random variables is the probability generating function. We can, quote unquote, quickly write down the expected value and standard deviation of the compliance measure. So we know the mean, standard deviation is the square root of the variance, and probability generating function of the compliance statistic that's broadly used throughout healthcare. Why we want the probability generating function is, one, it's a proof that the compliance is not binomial because it doesn't have the functional form it would have to have. And two, you can take successive derivatives of that in theory and get and set S equal to 0 and actually get exact probabilities. We tried to go down that path for a while, hoping some sort of pattern would set up, and we could use some sort of induction approach, but it didn't play out. So this is the exact probability distribution of compliance to bundles. And it has to do, there's a lot of summations, and I'd be happy to send you the paper that derives this, but basically just realize there are a lot of summations, and what we're doing is summing up all possible ways that 30 out of the 40 care elements could have been successfully administered. So there are 40, choose 30, and I'm not good doing that factorial division in my head, but there's a large number. So you're working through a lot of these summations, and there are actually a lot of every one of these terms inside the summations is a probability calculation that if you have a large enough sample, you're going to have to compute using recursion anyway. It'd be nice to just say, listen, Jim, you're sort of splitting hairs here. Can't we just, in the back of the room, squint and say the whole thing's binomial? You had 40 opportunities, and let's just give every one of those opportunities some weighted average of all of the probabilities and just call this thing binomial. So I'm going to call that the naive binomial approximation. Couldn't we just say, in the long run, everything's normal? And set the mean and the variance equal to these means and variances and just use Gaussian's normal curve and go from there. So in theory, maybe. This is why it matters. So here's a comparison of the exact distribution and the binomial approximation. In dark blue, for a particular situation, is the exact probability distribution of bundle compliance, the formula we just saw. And in light blue is if we just said you're getting a little too deep here, and I'm just going to henceforth just forget this and treat this as binomial. So considerable difference. Just looking at where the tails touch down, and think about how all statistical methods somehow, the tails are important in hypothesis tests or confidence intervals or control charts. If you look at this difference in the tails and think about how that would extend to a control chart over time, these inner thresholds are the correct upper and lower probability thresholds, control limits, and these outer limits are the incorrect. So in this setting, we could have an improvement and completely not know it and conclude we have no improvement whatsoever. The opposite is also possible. This is just one example. So we have opportunity to make both types of errors, and in some cases it's significant. And this is important because stepping back, the purpose is to accelerate the improvement of healthcare processes. And by all means not to decelerate the improvement of healthcare processes. The other thing to point out is there's some skewness here in the correct distribution. So using the normal distribution, which is perfectly symmetric, they don't fully align. So you may be sitting there and comparing the correct and the incorrect, and visually you're seeing that they don't match. Okay, so we can move on. I just want to point out, mathematically, there are some things we could compute to quantify the degree by which they don't match. But it comes out kind of the same. And later on, I'm going to refer to these metrics, so I'm just pointing them out now. The other thing to point out is notice how much tighter the correct distribution is than the incorrect distribution. And if I do this enough, it almost always seems to be the case. So a student and I worked through, it took a while, a mathematical proof of under-dispersion. So the correct distribution is always under-dispersed, has a smaller standard deviation than the binomial distribution, always. Which means if we develop statistical methods based on the correct distribution, we'll always have tighter confidence intervals in terms of the half-widths, larger power, smaller p-values, tighter control limits. We will always make the correct decision faster. So that's the takeaway. So here it is, without deriving it, in the paper. The confidence intervals always smaller, hypothesis test always more power. A particular type of hypothesis test, which is the most powerful type of hypothesis test, called the likelihood ratio test, always more powerful, and formula for the upper and lower control. And so once you know a probability distribution, you can basically develop whatever statistical method you want from that. So we have a whole suite of control charts. Simple control charts, exponentially weighted moving average control charts, and cumulative sum charts. So the underlying theory to cumulative sums are really this thing called the sequential likelihood ratio test, or sequential probability ratio test, SPRT. There are two types of tests. Originally developed in the 20s. The first type is a one-time test, like a hypothesis test. And it's more powerful than the types of hypothesis tests we use. So with the same sample size, we can have more power. We can have the same power with smaller sample. Faster improvement. The other type relates to control charts, and in World War II, Wald and colleagues extended this to the context of a control chart. Just like Schuhart extended the whole idea of hypothesis test to a control chart in the 20s, Wald extended the concept of this type of hypothesis test to a type of control chart, which is the underlying basis of what we commonly call Q-sum charts today. So I want to show you something, not to step through it, but so that you understand a little bit of the theory, and also so that I can point out one of several ahas. So the way these likelihood ratios work is they are a ratio of likelihoods. So the likelihood that's in the denominator is the probability of observing all the data that we actually collected if there's been no change. So it's a product. If we have 100 data, it's the product of 100 probabilities. If the first value is a 3, and the second value is a 7, and the next value is a 4, what's the probability of getting a 3, a 7, a 4, and so on? If there's been no change in our system. In the numerator, you have the product of these 100 probabilities if there has been a change. So it's a probability in the numerator and denominator, and it's a ratio, and that's it. And then you compare that to thresholds. Now, classically, for convenience only, people take logarithms and do some algebraic rearrangement. There's no need for it. Kind of nicety is, after a little work, you can create this term here. This is the sum of all of our data. It's the accumulation of data. It is the Q sum. This is the cumulative sum. So it's possible to isolate a cumulative sum and compare that to what are analogous to upper and lower control limits. So we've derived a whole family of these types of things for this distribution, for the exact distribution that applies to risk-adjusted data and bundle data. And there are different variations because in one case we may be looking at one patient at a time and knowing whether that patient developed an SSI or not. That's the upper. And the third case is when we just have a hunk of data and all we know is 30 out of the 40, but we don't know which patient. And so this is common context. I know my composite measure, but I don't know any of the underlying data. And so there's a whole talk in and of itself to derive these things, but here they are. What's interesting is there's absolutely, in none of these cases, no way to isolate a cumulative sum term. So the SPRT is still valid. We just can't rearrange it. We can't plot this thing as a cumulative sum term. And that's just interesting to point out because frequently I'm hearing and seeing in the literature people refer to risk-adjusted Q sums. So technically, I mean, you may have to stare at this a little bit more. There's no such thing as a risk-adjusted Q sum, an exact risk-adjusted Q sum. It doesn't exist. Maybe there are some approximations, and maybe those approximations are fairly good, but there's no such thing. Risk-adjusted SPRT exists. So here's an example. Surgical site infection bundle, different rates. Here's a control chart. And for reasons that are beyond what I want to go into, the center line actually can change over time. It's not a constant. So green is correct, red is incorrect. Red is based on the binomial, green is based on this exact distribution, which we call the J binomial, because there are J categories, J elements. So it's a little visually difficult to look at. You can standardize this thing and put it on what's similar to a normal 0-1 standardized scale. And now your limits are plus and minus 3 standard deviations, and the data differ. But again, green is the correct plot, and red is the incorrect. And you can see that they differ. How important is that? We can construct an exponentially weighted moving average chart of this, which has more power. That's the reason we would want to do that. And the same data set, now we're saying things have gotten worse or things have gotten better using the incorrect binomial assumption, whereas using the correct method, we really don't see that type of signal. So this may just be an anomaly in this particular data set. And so the question is, can we analyze the relative performance a little more theoretically? Here are just some other bundle examples. Again, just looking at some plots in terms of correct and incorrect. Sometimes it matters a whole lot, sometimes it doesn't matter that much. Here's a bundle where the dark blue is correct and light blue is incorrect. One case, we're drawing one type of wrong conclusion as to whether there's been a change or not, and in the other case, the other type of wrong conclusion. So doing it right matters in some cases. Here's a sequential probability ratio test, the Q sum, if you will, plotted over time. The 3 plots are exactly the same data, one using the correct calculations, which the way we interpret values below this lower control limit is whether there's been no change in the process or things have gotten better. And we would like the data to get down into this region as fast as possible. Correct method gets there first, using the normal approximation soon thereafter, using the binomial method that that most of us would use, available in software, takes an extra 12 points. If you're plotting monthly, that's a year. And these are some examples, not in the bundle context, but in the risk-adjusted context. Surgical site infections, this is mortality data, and some other data having to do with drug abuse, and I won't go into the Shipman data. If you're familiar with that anecdote, you can see what's obvious here, where there's been an increase in a physician assisting his patients into the absorbing state of mortality. But up here is some risk-adjusted mortality data that we've been working with somebody we've been doing this work with. And green is the correct, so green is the answer key. And blue is the normal approximation, which trends reasonably well, and red is if we use the binomial method, which is always drawing the wrong conclusion. Points above that upper line indicate there's a change, and points below the lower line indicate there's been no change. So it matters, at least in these anecdotes. So let me quantify a little bit why it matters, and then wrap up with some implications. The OC curves. So those were just some examples in data sets from organizations that we work with. So we have computed the precise operating characteristic and average run length curves to compare these methods. And narrower is better. So for Shewhart charts, we design the chart because we want an in-control average run length of 370. That's just what we picked. It's the industry norm. Because we think that's a reasonable false alarm rate to live with. In other words, if there's no change in your process, every 370 plotted points, you'll get a false signal, a type 1 error. Okay, big deal, I can live with that. If that's going to give me a faster detection of changes. So what's interesting is when you do it wrong, quote unquote, using methods readily available in software, the curves are just much, much wider. So it's going to take a long time to detect an improvement. In the probability ratio test context, there are actually two performance measures that matter. Back to this. So line indicates no change in the process, and deviations left or right indicate process gotten worse or better. Interested in two things. Here is on the bottom is time until a decision is made. So the decision that's made is there's no difference between hospital 1 and hospital 2, or your before and after. Or there is a difference. Doesn't matter which decision. Just time until I can make a decision one way or another. The normal approximation actually makes a decision faster than the binomial, than the J binomial, and the binomial is just sort of atrocious in a relative sense. But the J binomial is making the right decision more frequently. So we would accept in this case type 1 error rate. This was what we were targeting, a type 1 error rate and a type 2 error rate. And we're getting exactly the performance we want in a reasonable amount of time, as opposed to getting nowhere near the performance we want and taking a lot longer. So some other examples, same takeaway every time. We folded this whole approach into cluster detection, because when you're looking for clusters of diseases geospatially, you may miss clusters or over-detect clusters just because there's a higher or lower occurrence of at-risk people in those particular areas. So there could be almost an inverse cluster, the appearance that we have a significantly lower occurrence rate of a particular disease in an area, where in fact you have a cluster once you risk adjust. So we've been looking at that context, and we have greater separation of the null and alternate distributions, which equates to more power. So I led you down the golden path a little bit, and it's time to make a confession that the problem is computation speed. So J is the number of bundle elements or different buckets, stratifications in our risk adjustment scheme, and N is the number of patients in each of those buckets. So in small cases, this is computation time in seconds. No big deal. But quickly, this thing just gets out of control. So anywhere, a reasonable sized problem, we run into cases where it takes 10 minutes to 5 hours to compute one probability. We're getting it exactly. That's the good news. So in SPRT, if you have 100 pieces of data, you have 100 probability calculations in the numerator and the denominator. So that's 200 calculations times 5 hours. By the time you know there's a problem, you're not going to be able to react to it really quickly. And the cluster detection method, we're using a variation of Koldorf's scan statistics. You're computing thousands of probabilities. So that's the bad news. So let me rescue myself a little bit. There are ways to approximate distribution. And the most success we've had have been using cumulants in different types of expansions, polynomial expansions, but Charlie expansions and Lagrange polynomial. And saddle points. Saddle points are giving us excellent results in the tails, which are important in statistical methods, but really lousy performance in the body. And the best results we get across the whole probability distribution is with the Graham-Charlier expansion. I'm not going to go into any details because there may be some people familiar with that, but the point is we can approximate these things. Here are 3 cases. Reasonable 4 elements through 10 elements, or 10 strata and a risk adjustment, reasonable sample sizes. And let me just look at case 3. This is CPU time. If we use the exact distribution, 5,000, so roughly, 600 seconds would be 10 minutes. So basically about 100 minutes to compute a probability. But with these approximations, we can compute a probability in 0.03 seconds, which is pretty good, and probably just as good as a normal table lookup, even in a computer. And these sorry, I keep losing my mouse, are the performance measures in terms of how accurate the approximation is to the exact distribution. So these are those things when I said there are ways to quantify the tail. Something close to 0 means tails just overlay perfectly. So we're getting highly, and you can see this in a plot down here. Here's a plot for one. This case, case 3, 3 distributions, the exact distribution and the approximation, and just a Monte Carlo simulation that we let run for about a week. And you can see it doesn't matter which is which because they all agree. So we're getting highly accurate results very quickly. So there's sort of too much to convey, but the summary is really adherence is a huge problem in healthcare, and variance. And the desire is to improve. And from my perspective, what can our group lend to this sort of national effort? And anything we can do to accelerate improvement, I think, is a contribution. And to minimize, that's the message I don't want to be lost, to minimize the non-uptake of true improvements, which I have no way to prove is happening, but just from sort of this presentation, it's sort of almost certain it's happening. The exact probability model, so our approach was we developed the exact probability model, and that's the exact probability model of risk-adjusted data and bundle compliance, and then use that to develop more powerful methods. And just as an aside, I didn't have any time to really mention it, but in a similar way, composite metrics have more power than this all or none proposal, for reasons I'm happy to explain offline. And this all or none thing is an excellent idea in terms of motivating the need for change. But it's not a good idea in terms of statistical analysis of the data to accelerate the improvement. And we actually have a paper really comparing, but you get the same thing with the OC curves. The composite OC curve is far better than the all or none OC curve, and that's the takeaway. So thank you again for sharing some of your Friday afternoon. I think we should end there and maybe entertain some discussion or some questions.
I think a couple of questions would be good.
running long. We have no takers. This is a very detailed one, but if I understood it, the statistical model assumes independence between elements. So, for example, you might have a nurse's shift where they tend to not give beta blockers and not do something else.
Right.
And they tend to go together. And would that be missed, and is that an issue in calculation?
Well, it's a question so the comment was not only could there be heterogeneity between the elements, but between who's delivering those elements or who should have delivered those elements. So from a technical perspective, sort of the beauty is done. The problem would be data capture. So conceptualize it as if you had 2 different nurses or 2 different shifts and 4 elements, you now instead of J equals 4, J equals 8. You basically have 2 versions of element 1. So mathematically, we just fold all of that in. It would just be a data capture issue. I never thought of that before, though, so thank you.
Oh, Jim, so I have a question. When I hear this, I get a little bit concerned. So, you know, regions of kind of frontline clinical staff are being taught to use control charts to detect whether the work they're doing is changing or not. Mark explained down there teaches a course at TDI, I think IHI teaches people to do this. There are macros programs, for several people.
Right.
Are these all wrong, or are this kind of a large misdirected effort, and we're kind of using the wrong tools and not using them well enough? It's one of the things I wonder I see with you.
Well, I mean, I don't think it's as bad as the problem we have with the healthcare system, but there's room for improvement. So the methods are right, but my concern about the use of statistical process control charts in healthcare is becoming widespread. And my concern is that the right methods get disseminated and spread broadly. And I mean, to your concern, no, there's a lot of bad advice being spread. A good example of that is the widespread use of this thing called an individual's control chart. I advocate that it just be that capability be removed from all software. I mean, it always results in poorer OC curves. That's the reason, not because geez, I just don't like it esoterically. Poorer OC curve. So it always comes down to that for me. But in this context, I'm seeing a lot of folks use commercially available software to construct control charts through the menu on bundle compliance. So you just pick the P control chart based on the binomial distribution, and here it is. So that control chart technically is wrong. So the question is how wrong. More often than not, but not always. But most of the time, the limits are going to be wider than the true limit should be. So more often than not, the incorrect conclusion that we're making is not that there's been a change when there's been no change, but we're not detecting or verifying improvements. Right? So that's the sensitivity problem. Right. So I think to some extent we're slowing things down. Yeah.
I mean, how much is this going to be like the razors in the operating room? People learn to do this now, sort of change the way people do this because this is complex.
Well,
I mean, can simple to use programming be modified to take into account more complex models?
Well, so. Aside from me, I don't know anybody that's calculating these things by hand, much less putting the formulas themselves into an Excel spreadsheet, right? So it's just a matter of getting it in software. So if this were an option in something that were freely available with shareware that you could pull down from our website, from the IHI website, from TDI or anywhere, and here's the macro or here's the piece of software. So we're actually sort of seeking support. We have some pretty kludgy stuff and some templates we want to get put up so people can make use of them. But we'd love to basically embed all this stuff. and get people using more powerful tools.
Jim, I think we better
Yeah.
sit there. Thank you.